We now move on to logarithms, and our starting point is the meaning of a logarithm. So if we have 4 squared equals 16, for example, and we want to set this out in log form, we would define the exponent 2 to be the logarithm of 16 to the base of 4. So it would look as follows: log to the log of 16 to the base 4 equals 2. And what you will see is what a logarithm is. It's the power that a base must be raised to attain a particular number. So here our base is 4, and the logarithm tells us the power that we have to raise 4 to in order to get 16. And we know if we raise 4 to 2, in other words, if we square 4, we will get 16. We're now going to look at logarithmic functions in a little bit more detail. And to understand logarithmic functions, we need to also work with our exponential functions. So, for example, if we have y equals a raised to the power of x, we can generate the inverse, which is just swapping the x and the y around. Okay, so we would now have x equals a raised to the power of y, and this here would be the inverse of this function here. All right, so before we go through the table, let's just take a look at what's written down here. So we now have the inverse for this exponential function, but we do not write its inverse as follows, okay? Since y is still the dependent variable, and convention tells us it goes on the left of the equal sign. So rather, we set this out in log form. Y equals the log of x to the base a. If we go back up to this table now, we can work with these functions. All right, here we've got y equals a to the power of x, and then in this column here, we've got the inverse, okay, where we've actually set it out in either form. Now let's just calculate some values. And first of all, we look at an example where the base a equals 2, okay. So what we are saying here is if the base is 2, if a equals 2, when x equals 1, 2 raised to the power of 1 would make y equal to 2. Okay, so we've now worked with the exponential function. Let's now work with its inverse. And remember, with the inverse, we are swapping the x and the y. So let's do that. Let's say here y is 2. So what if x is 2? Okay, and either working with this function here or with the log function, which you need your calculator to work with, if we have 2 as the base, all right, and if x equals 2, all right, obviously then y would be equal to 1. So this is what we can see here with these inverse functions. When x is 1, y is 2, and then for the inverse, when x is 2, y is 1. And then down here is another example, okay, just with some different numbers. We're still working with the same functions, but now assuming that the base is 5. So if the base here is 5, if a equals 5, and let us say that x is 2, 5 squared would make y equal to 25. Then for this function here, all right, if you to work it out with your log function here, if we let x now equal to 25, you will calculate a value of 2 for y. So again, we see for this exponential function, x is 2, y is 25, and then with the inverse, we have x equal to 25 and y equal to 2. On this slide, we illustrate the graphs of the two functions that we looked at on the previous slide. And here we have the exponential function and the inverse in the logarithmic form. And for various values of x, we have calculated the y value for each function. So if we have a look at the exponential function first, we can see, as we saw on the previous slide, where x equals 1, y equals 2, and then with the logarithmic function, where x equals 2, y equals 1. All right, with them being the inverse of each other. And what that means is when we draw these two graphs, they are effectively the mirror image of each other. Two numbers are widely chosen as bases for logarithms. The first one of these is the base of 10, which when we work with a base of 10, the logarithm is known as the common logarithm. And we see some examples down here. For example, the log of 100 to the base 10 is equal to 2. Okay, and so that's quite computationally easy, and we can quite easily see this example or the answer, because remember, with logarithms, we are working out the power that a base needs to be raised to in order to get a particular number. Okay, so here the base of 10 needs to be raised to the power of 2, okay, 10 squared, and that will give us the number 100. Okay, and okay, we see that set out here just to make it a little bit easier. 10 squared equals 100. And similarly down here, the log of 1000 to the base 10 is 3, because 3 is the power that 10 needs to be raised to in order to get this particular number of 1000. The other number that is commonly used as a base is e. So for example, if we have this exponential function, y equals e raised to the power of t, and we want to set this out in log form, then the base would be e, and whenever we have a base of e, we refer to the log as the natural log, and we can use ln to indicate it's a natural log. So what ln is standing for is log to the base of e. All right. Where working with the base of e becomes quite useful is if we are given an expression like this, e raised to the power of x, where x is any real number, we can automatically read the exponent x as the natural log of e to the power of x. So in other words, if we're now working with the natural log of e raised to the power of x, then this exponent x would be the natural log in this case. So some other examples here where we have an expression where we've got e raised to the power of 3. 3 is the natural log of e raised to the power of 3. Okay, so 3 is the natural log in this case here. If we jump down and have a look here, we've got the natural log of 1 in this case. But remember, anything raised to the power of 0 is 1, so we can rewrite this as follows. Okay, if we want to write it out in full, it's the natural log, so it's log with a base of e, and the expression here is e raised to the power of 0. Okay, so the exponent in this case is 0, and that exponent, that 0, would be the natural log of e raised to the power of 0. Okay, so just seeing why it's quite useful, quite handy when we start working with a base of e. Looking now at some rules of logs, we look at these three here: log of a product, log of a quotient, and log of a power. And we've expressed them using natural logs, but they also apply when we have a log to some other base, for example, b. So if we have the log of a product, here we've got the natural log of u times v. We can separate these out, and we end up with the natural log of u plus the natural log of v. Log of a quotient, where we've got u, the natural log of u divided by v. Here it would be the natural log of u minus the natural log of v. And the log of a power, if we have the natural log of u raised to the power of a, what we can do with that a is bring it right to the front. Okay, so in front of the log sign, in this case the natural log. All right, so these are rules, and we use these in our calculations. Some fairly simple calculations shown below. So here we've got the natural log of u times v, and v is raised to the power of a. So applying the product rule as a starting point, we would have the natural log of u plus the natural log of v raised to the power of a, and then we can apply the log of a power, and in our final step we'll just take this a to the front here, as you see here, before the natural log. All right, and here we've got the natural log of a times by e raised to the power of 7. Applying the product rule, where we have the log of a product, we can separate this out and have the natural log of a plus the natural log of e raised to the power of 7. And remember from the previous slide, when we have an expression like this, e raised to the power, where what we have in the power here is some real number, then that value here would be the natural log of e raised to the power of 7. So in other words, the answer here would be 7. The natural log here would be 7. Okay. And then finally, the natural log of e squared divided by c. Using the log of a quotient, we would have the natural log of e squared minus the natural log of c. And similarly to the example above, the natural log of e squared would be 2. All right, so following these rules obviously makes it quite easy or a lot easier when working with logs. One final thing to note is if you are given something like this, y equals u plus v, you cannot apply logs to each of these terms here. Okay, what you need to rather do is group what's on the right hand side and take the logarithm of each side. Okay, this here will give you the correct answer. Doing it this way is incorrect and will give you the incorrect answer. Okay, so for example, the natural log of 5 is not going to be equal to the natural log of 2 plus the natural log of 3. Rather, the natural log of 5 will be equal to the natural log of 2 plus 3, which obviously would be equal to 5. Let's now work with an algebraic application. If you are given this here, a times b raised to the power of x minus c equals 0, and you are asked to find x on its own, what we can do is use logarithms in solving for x. So if we start, first of all, by taking c over to the right-hand side, and we then transform the exponential equation into a linear equation using logarithms. In other words, we take logs of both sides, okay? Then using our rules of logarithms that we looked at on the previous slide, remember here we've got a times b raised to the power of x. So we can separate this out, this product, and we can take the natural log of a plus we would have the natural log of b raised to the power of x, and then because of the power rule we can take this x to the front here, which then equals the natural log of c. All right, and then taking the natural log of a across to the other side, all right, and then dividing through by the natural log of b, we end up with what we were asked for, which is x on its own. What we also want to be able to do is calculate derivatives, and this is for both our exponential functions as well as our logarithmic functions. So we touched on the exponential functions earlier, and we looked at how we can calculate the derivative. So let's take another look here just to remind ourselves. If we have this exponential function, y equals e raised to the power of t, and we are asked to find the derivative of y with respect to t, what was really useful here is that it was its own derivative. So in other words, the derivative of this function here, e raised to the power of t, is in fact e raised to the power of t. Now looking at the log function rule, and here we have a natural logarithm. We've got y equal to the natural logarithm of t. So remember, we've got e as the base here. And if we want to find the derivative of y with respect to t, this derivative is 1 divided by t. So the two rules of differentiation that we saw on the previous two slides were fairly simple, and we were dealing with the variable t when we looked at the exponential function as well as our natural logarithm. Now we want to generalize these rules so that we can also work with a function of t. So instead of just having a variable t, we would also like to be able to work with a function of t. So in the case of an exponent or exponential function, if we were to have y equals e raised to a function of t, how would we find the derivative? Okay, how would we find dy dt? Well, our rule, which we did see earlier, would be to find the derivative, okay, of this function of t multiplied by what we have here in the brackets, okay, e raised to the function of t. All right, and if you recall from our previous slide, this derives from a chain rule application, okay? In the case of the natural logarithm, instead of just having a log of t, if we are having the natural log of a function of t, how would we find the derivative dy dt? And this rule tells us that, first of all, we have in the numerator the derivative of this function with respect to t. We would need to calculate that, and then in the denominator, we would rewrite what the function of t is. Okay, so fairly straightforward. To understand this rule here, okay, we are also using a chain rule application. So in other words, if y is the natural log of a function of t, and we set this function of t equal to u, so now we would have y equal to the natural log of u. All right, to calculate dy dt, we would first of all find dy du. Okay, so that would be working with this part here, dy du, and from the earlier rule that we worked with for derivatives, finding the derivative of a natural logarithm, remember the answer is simply 1 over u, or the derivative is simply 1 over u, so that's what we have there. Okay, and then du dt, okay, u is a function of t, so we would need to find the derivative of this function with respect to t. Okay, so if we set this out now, we would have the derivative of this function t in the numerator, and we would have u in the denominator, and u, remember, stands for f of t. Let's work through some examples now. If we have y equal to the natural logarithm of at, where our at is our function of t, okay, so finding the derivative of y with respect to t, okay, when we are finding the derivative of a natural logarithm and we have a function of t, remember we have to find the derivative with respect to t, okay, of f of t, and then we have to rewrite f of t in the denominator as it is. So if we find the derivative of at with respect to t, okay, quite simple, just going back to the power rule that we learned about when differentiating, we would have t to the power of 1, and we would end up with a, okay, finding the derivative of this function with respect to t, we would end up with a, and then rewriting the function in its original form, at, that would be in the denominator, and the a's would cancel out, and we'd end up with 1 over t. Here we have another example where we have the natural logarithm of 3 times t and 3t. This is our function of t, and the same approach again, dy dt. Right, here's our formula. We need to find the derivative of this function 3t with respect to t. So that would leave us with 3, and the function in its original form is 3t, which gets written down here. In the denominator, again, the 3's would cancel out, and we're left with 1 over t. We just need to remember that the examples we see up here, okay, where we've got, for example, the natural logarithm of a value times our variable, okay, is quite different from if we have something like this here, where 3 comes before the natural logarithm. Okay, so this would be 3 times the natural logarithm of t. So finding dy dt, we would need to treat our 3 similar to how we treat a coefficient whenever we are finding the derivative. Okay, so for example, if we look at the bottom here, y equals 3x squared, okay, we would keep the 3 and find the derivative of x squared and then multiply the 3 by the power, in this case here. All right, in the case of a natural logarithm now, we need to apply the rules that we use with natural logarithms, but the point is we leave the 3 as is, multiplied by what would be the derivative of this natural logarithm here, and in this case the answer would be 1 over t. Okay, from the earlier rule, the derivative of the natural logarithm of t would be 1 over t. So our answer in this case would be 3 over t, which is quite different to what we had up here, 1 divided by t.